Hello everyone, my name is Muhammad Al-Ghazah, and today I'll be talking about my project, which is on the synthesis and magnetic study of thulium manganese 6 tin 6-X gallium X. Modern electronics use silicon chips which are currently facing difficulties in making faster, thinner, and more energy efficient devices. Silicon chips use the charge of electrons to process information. However, electrons also have a property called spin. In magnetic materials, electrons spin can order over a long range, making magnetic structures. The conventional magnetic structures, such as in iron, are difficult to manipulate with electric current. So there's a great deal of interest in new forms of magnetic structures that can be easily manipulated and can thus be applied in spin-based electronics. I researched this specific compound because an interesting magnetic property was reported in polycrystalline form. However, to completely understand the magnetism and look for potentially interesting magnetic structures, studies in single crystalline form are required. This is the schematic of the structure of thulium manganese 6 tin 6. It consists of thulium and manganese, where you can see in this photo, these are the actual elements, which are both magnetic and form layers going along the C-axis. The green sphere is thulium, black is manganese, and the rest are tin. Tin in this particular layer can be replaced by gallium, which has a smaller atomic radius than tin. We know this by looking at the following periodic table. The gallium doping will then change the magnetic interaction between different layers and allow us to manipulate the magnetic structure. Our goal is to manipulate the spirals in the parent compound to stabilize a magnetic structure that can potentially be manipulated very easily. To synthesize my crystals, I used the flux method, where all of the following elements were put into a crucible and put through a series of changes in temperature. In this case, tin is the flux, since it allows the other elements to melt at a much lower temperature. The reaction was then carried out in a non-reactive atmosphere inside the furnaces shown here. Tin dissolves both thulium and manganese below their melting point and allows all the elements to form a solution. Then lowering the temperature oversaturates the solution and the crystals form. So this is a picture showing the process, and this is a crystal that I was able to grow in my research. The compositions I grew included thulium manganese 6 tin 6 and gallium doped 0.5, gallium doped 1, and gallium doped 1.3. The structure of the crystals was then verified through X-ray powder diffraction, which gave the data shown in this figure here. After verifying the structures and learning the compositions, I then measured the magnetic properties of the crystals. In this figure, it shows the data I got using the quantum design PPMS available at the Gamir lab. The top figure shows where I measured out of in the plane, where the bottom figure shows where I measured out of the plane. What we see here is that all the compounds show a sharp transition at around 350 to 375 Kelvin, which is shown in both figures. This is the temperature at which the compounds become magnetic. In the top figure, the overall magnetic moment is larger for all the compositions except x equals 1.3 when compared to the bottom figure. This tells us that the spin in these compositions are in the plane. But when looking specifically at x equals 3 shown in green, in the top figure, the moment is larger above 200 Kelvin and small below that, but in the bottom figure, we see the exact opposite behavior. This tells us that the spins from 200 to 350 Kelvin are in the plane, but when the temperature is below 200 Kelvin, the spins reorient out of the plane. As of this semester, I have been able to grow the crystals, verify them, and measure some of their magnetic properties. However, there are several things yet to be done, such as measuring magnetization, resistivity, and Hall effect. This will tell us if there are any interesting magnetic structures, and following that, neutron diffraction experiments can be done, which will allow us to figure out the nature of the magnetic structures. I would like to thank my mentor Dr. Gamir for allowing me to conduct this research, and I would also like to thank Hari Bandari and Peter Siegfried for their assistance inside and out of the lab. Thank you very much for listening.